First, we will look a little bit into the history of these machines, and we use the PDP1 here as sort of our central starting point. The PDP1, designed in like the late 50s, 59, sold starting in 1960, and about 50 were built and sold by DEC. And I think it's a very good starting point to explore this whole history if you're interested, because we then have a couple of PDP models branching out from this, but there's also a history to the PDP1.
So the DEC is the Digital Electronics Corporation?
Digital Equipment Corporation.
Equipment Corporation, right. Okay. And they were obviously a computer manufacturer in America.
Yeah, they didn't call it computers back then because that evoked notions of IBM style, like payroll business machines, very hard to access, like you give your punch cards to someone and so on. And these are a different tradition, very interactive and more personal. And the PDP-1 was sort of the first one that you could buy in that lineage. The PDP-1 was an 18-bit machine, you can see it here, 18 bits, and 4 kilowords of memory originally. So a word is, again, 18 bits. It didn't have any bytes yet, that came in the mid-60s. So after the PDP-1, which was a little bit more experimental, DEC was a startup essentially at that point. When they had more customers, they had different needs, and the company was expanding. So the first model after the PDP-1 was surprisingly not the 2 or 3. That was like an old business strategy that didn't pan out. But it was actually a PDP-4, which was also an 18-bit machine, but not really, not compatible with the PDP-1. Like they had the same peripherals to some degree, but not quite. And they reused these architectures again. They built new machines that were more or less compatible. So the 7 was the next, and that one is perhaps a bit famous for being the machine that Unix was developed on by Ken Thompson, 1969. They again built in a machine in that family, the 9 and the 15. We're not going to talk about that.
So they're just kind of different capacities, or?
Yeah, so essentially they rededicated, like they flipped one bit from being an address bit, from being an instruction bit to being an address bit. So you get 8 kilowords of memory on the PDP-4 and in this family, but you get only half of the instruction space. And so in Unix, you see that because the kernel has 4 kilowords of memory and the user has 4 kilowords of memory. And with a PDP-1, you would only have like 4 kilowords. The time sharing on a PDP-1 was done a bit differently.
So yeah, kilowords is a new one to me.
Yeah, people are not used to kilowords anymore.
1024 words then?
Yeah,
okay.
Right. So that was sort of the first thing that that they built, and afterwards came the PDP-5.
What sort of things were these used for? Who were their customers?
So the initial idea was to make a cheaper PDP-1 essentially, and also use it for things like process control, lab equipment, that sort of stuff. Things where the computer is part of a system and not just the system itself crunching numbers like a mainframe would do, like doing scientific, I don't know, weather simulations or whatever, and eventually you'd have the result. But it was something that, you know, talked to the real world. Mm-hmm. And so there was a smaller family, which is kind of a stripped down 18-bit family, condensed into 12 bits. That's the PDP-5, 8, and 12. So these are very minimal and really just to like more of the lab equipment type and process control, even though people did time sharing and such on the PDP-8 as well. And it's a very popular machine. There's a big PDP-8 fan community. And the PDP-8 was the first that Oscar made. And on the other end, we have the PDP-6 and the PDP-10. So the PDP-6 and 10 were 36-bit machines meant for time sharing, such that multiple users could use the machine at the same time. Also sort of designed to run Lisp well, which was a popular programming language in AI circles and around MIT where these machines came to be. And yeah, so that is like the on the wide end of the word size 36 bits.
I'm just going to ask a question if that's all right, because obviously you've mentioned the word AI, right? And we're now talking about the 1960s. I mean, this is, become massive nowadays, but it isn't this, what we're going through now wasn't the start of AI, was
right. AI at that time meant something like symbolic differentiation or chess programming, stuff like this. So symbolic AI, good old-fashioned AI, not the neural networks. I mean, the neural networks go back quite some time, but this was not really what people did because the computers weren't there yet. So this is sort of the PDP family, and there's one important piece missing, which is the PDP-11, introduced in 1969, like around 70. And this kind of pulled everything, or almost everything, together a bit. So it's a single architecture that has small machines, PDP-1105, for things like what a PDP-8 would do, maybe. But also bigger machines, maybe a PDP-1140, which ran Unix, or on the higher end, a PDP-1170, which was quite a capable machine. It did not quite replace the PDP-6 and 10 style machines, but they later built the VAX, like a 32-bit reinterpretation of the PDP-11. This was 16 bits. And so they had these two as their flagships, essentially, and this became like ancient history, which is why people don't know so much about them anymore. And these are very familiar. These have bytes, like byte addressing, which people take for granted these days, but these don't have bytes yet. These are all word addressed.
So I mean, they were pioneering machines, those ones, but basically we're going to have a look at what came before.
Yeah, I mean, everyone was pioneering at the time. You had no choice, but people had to figure out what computers should be like. For instance, Gordon Bell, who was the architect on essentially all of them, except for the PDP-1, said this 18-bit line was a mistake because it was not compatible with the 18-bit PDP-1, and they didn't appreciate the portable software yet. Being able to run.
Being able to write.
Right. They thought, oh well, you just write the program for the new computer, and then. But yeah, software quality, like the value of software was not on people's minds apparently back then.
And I suppose when I say pioneering, I guess I mean they laid some of the foundations that we still use today. But yeah. Yeah,
like the PDP-11 and VAX are like very normal computers from today's points of view. You can read PDP-10 assembly or VAX assembly, and it's not too foreign. Whereas when you go back to these older machines, it becomes a bit less familiar. But on the other hand, they are also very simple. Like the PDP-1 is not a complicated machine, for instance. So you can still understand it. It just takes a little shift in the perspective, perhaps. Mm-hmm. And so there's also prehistory, which we're not going to cover, but the PDP-1 was preceded by the TX0. And these were one-off machines now that we're talking about. These were like production machines that were sold, even if maybe not too many. But the earlier stuff only existed once. So the TX0 was also an 18-bit machine, but much simpler than the PDP-1. There's also a TX2, which was a bigger 36-bit machine, famous for being the machine that Sketchpad was written on by Ivan Sutherland, the first CAD system, you might say. And it goes back a little further to the memory test computer, which was really part of Project Whirlwind. So Whirlwind 1 was that machine, originally to do cockpit simulation, but it didn't really pan out, and they built a digital computer instead. I call it the first microcontroller, except it took up a whole building. But essentially that was the idea, to have a computer that interacts with the real world. So this is where it starts.
Well, what era is that then, Whirlwind?
Whirlwind 1 was operational, more or less, or became operational during 1950. And
so it's kind of post-war kind of things.
Right, they had difficulty with finances because the war stopped, and well, luckily for them, the Cold War started, so they got money again. Right. And that is how the Whirlwind 2, you might call it, but it's perhaps better known as the computer of the SAGE system, the ANFSQ7. That was like a bigger version of the Whirlwind 1, essentially, built all over the US for airspace monitoring. It never really had a purpose, because shortly after they had intercontinental missiles, and like they never got to use it, essentially. So yeah, this is the history that we're talking about. And the Whirlwind 1 was what core memory was invented for. Here we got modems, and like displays already were on the Whirlwind, and this kind of goes down into the tree. So we have this whole history of interactive controller type personal, perhaps, computers. And so again, the PDP1 is sort of our central piece here, and we will now look a little bit into what the computer, how it works, and what to do with it, how to use it, using the PDP1. We're first going to look a bit at the front panel, what it shows and how to use it, and then we'll use it to draw the circle that uses the algorithm that Marvin Minsky discovered, and also the Minskytron, which is based on that algorithm, which is a very nice looking demo. And it's also, you can play with the switches, and it's very satisfying to play with. So what you see on the panel, all these lights are almost all of the state that the PDP-1 has. All the internal flip-flops are visible as lights on the panel, which you need because if the machine isn't working, and back in the day the machine was not working quite a bit, you have to make it work again, and you have to see the machine state. This panel doesn't have all the lights. There was an I/O panel, and peripherals would have more lights and so on, but this shows everything important, really. So we have two registers up here, the program counter and the memory address. Program counter is the same as you would expect today. It's the address at which to fetch the next instruction. Memory address is the register that holds the address for the memory word that is being addressed by the computer. So it's just an address. And the memory buffer is the data that either came out of memory or was written back into memory. So at the end of a memory cycle, the MB register would show what is in memory at that location, shown at memory address. And the accumulator and in-out register are what the programmer uses. And as you can tell from the name, in-out is also connected to the peripheral equipment I/O stuff. So the accumulator is the arithmetic register that control with your program, more or less. And I/O was also used for like as an auxiliary register. Also, when we display a point, it will be X and Y coordinates. One register is X, one is Y. And the address in the basic machine is 12 bits here. But we have a memory extension. We can use up to 64 kilowords. 12 only gives you 4 kilowords, and 64 kilowords for the maximum what a PDP-1 could do. So here we have like a run light and a cycle light and so on. These run is obviously when the machine is running. It's not running yet. And this is internal flip-flops that we're not going to go into in much detail. The power switch obviously turns off the power and on again. The sense switches could be used by a program just to read like general user interaction. You can read them, and the program flags are kind of similar. They can be set and read by the program to its will, and they can also be connected to some peripheral equipment. Like when you use the light pen and it sees a spot, it might set the program flag for the pen here. And we have the instruction register. So 5 bits that encodes the instruction. So now let's put something into memory. We have the Minsky circle algorithm here. It's not a lot of words. And we have the symbolic assembly on the right here. And I just wrote down the binary code, an octal, that encodes these instructions. So you have to know octal, of course. Oh, and on the left we have the address where we put this into memory.
So because, just to remind me, that's a base 8, isn't it, octal?
Right.
Is that right?
So 3 bits are 1 octal digit. It's very easy it's very quick to get into, really. So if you have the upper bit, that's a 4. If you have the middle bit, that's a 2. And if you have the lower bit, that's a 1. And so if you have multiple, you just add them. So that's 5. And at some point, you just don't think about it anymore. You just read octal and toggle in binary, or you read binary. So let's do a couple of instructions manually with the front panel. We start at address 100. And the word that's supposed to go here is 7, all up, 6, which is 4 and 2, 1, and the rest zeros. Now pressing deposit up puts this into memory. We see memory address 100 and memory buffer 761000. Oh, actually I made a mistake. That's the second instruction. That's no problem. We could just change the address and put it in location 101 instead. Easy. But now we have to do the first instruction, of course. So that is 200113. So 200113. So you can already tell it's easy to make mistakes. And that is why I don't really want to do this on the front panel so much. It's very tedious. But just to make sure that we also check the examine switch, let's look at our previous word and press examine. And then we see our 761 again. So now let's do the rest not on the front panel, but actually using the debugger DDT. DDT is the debugger, and it's an insecticide, so a debugger. So I have DDT mounted as a paper tape in the reader. It will be above the front panel here. We have it on screen. And when you press read in, the machine knows the format of the tape and goes through it. And you can see the address being counted up here, where things are being put into memory. And eventually, it's going to jump into DDT. Okay, so now we're interacting with the typewriter here.
Would that have been the sort of speed a paper tape took to run, or is it?
Yes, it's the original speed. Like there are different numbers given, but 400 lines per second is about right. Something like 300, 400. Okay, so now let's confirm that what we have put into memory is indeed correct. So at address 100, we have exactly the instruction that I wanted to put there. And by pressing backspace, we can check the next one. And equals gives us the octal. And so now I just do the rest. I can do some in octal directly. This will be the next instruction. And the next one. And the rest one, the other ones, I will just do symbolically, because that's something DDT can also do. So we are now at 104, and that is supposed to be DAC 114, deposit accumulator. Okay, so now we finished putting this into memory using DDT, and we see by examining successive locations that we have this code in memory now, which is the one that I want to execute. DDT was quite popular on other machines as well. There is a whole tradition of these interactive debuggers. It doesn't start with DDT, but DDT is fairly well known. Okay, so we now finished putting the program into memory. We can examine the memory locations with DDT, and we see the code, which is the one I wanted to put in there. And now we want to start this program. One way to do it is with the front panel. So we stop DDT, because we're still running, so run is now off. And we put in our start address, which is 100, hit start, and there we see the circle.
So what's happening now is kind of the equivalent of find a point, print a dot there, move a bit, print a dot there.
Right, it starts with a single point, and essentially with a little bit of approximate trigonometry, you would move the point with a small angle. But if you approximate it, it spirals out because it's just an approximation. So Marvin Minsky's discovery was that you don't calculate the new point from the previous point, but that the x and y coordinates are sort of linked. And if you do the math, you find out that it actually remains stable. So that was a very cool discovery. And there is a program called the Minskytron, obviously named after Marvin Minsky, which is 3 of these circles kind of linked together. So one oscillator is connected to the second one, the second to the third, and the third one again to the first. And you have settings on the switches which control them, and you have a very cool demo. And this is exactly what we're going to do now. So we'll put the...
So this is where we use the magic of the emulator to load it back in, right?
Right. Oh, actually, no. Let's do one thing first. We want to perhaps punch this onto paper tape because we like this program and want to run it again without toggling it in again. So we go back into DDT, which is at 6000. So stop the machine, start there. We're back in DDT. And now we punch a tape. We start with a title, capital L, and we might call it circle. And we see it punched on the paper tape as just so you can read it.
So you know what that tape is.
Right. With tab, we go into punching words now, and our words start at 100, and it goes up to 114. And now we see the words being punched, and we just have to give it our starting location now, which is 100 or 100. There it is. And now we can like rip off the tape, which we do with the emulator here.
So you're basically saving that
right.
as a program.
Exactly. So we're now storing that. The file already existed. It's fine. So we now have our paper tape, which came out of the machine, and now we want to put it back into the reader. So here we go. There it is. And obviously we still have it in memory, but it doesn't really matter. So just read in. The tape goes in and it jumps into the circle program.
So that last instruction on the tape is basically run.
Right. It just executes the instruction from paper tape, really.
And on the tape, I think we've done a video on paper tape in Computerphile before, but each line is basically some code, is it?
Yeah, one word is 3 lines, and there's different formats. Like read-in has a special hardware format, but it's not the most space efficient, and so there's more efficient loaders. But yeah. But that's how it works. And that's how you would perhaps program the machine and punch a program onto tape. And yeah, very interactive and nice to use. You could, of course, use an assembler, but that's a bit more involved. Okay, so now let's go into the Minskytron. So we load this demo tape here and read it in. Takes a while. Oh, that's the snowflake, but we don't want that. We want Minskytron. It starts at 500, and it needs some initial switches. If we start like this, it's just very noisy, because all these shifts that are done in the Minsky algorithm, which is a very easy division by a number, a power of 2 number, we can set these shifts now. So let's just try something.
So you just randomly,
more or less random. I have some intuition, but not too much. But you can see how we have this feedback between these 3 oscillators now. And if you observe it for a while, it will go crazy. Or if you change the switches, you can just change them and hit start, and you get a different pattern. And you can really have fun exploring all these possible patterns here. And sometimes, like this is the typical display after some time, would just go crazy.
So PDP1, you're drunk, go home.
Yeah, exactly. But it's very, very fun to explore for sure, and I can really recommend doing that. There's a very good website where you can do it as well. Maßwerk Minskytron. If you Google Minskytron, you will find it easily. So kind of in a chaotic mode right now. Let's see. But yeah, this is what you can do with this very simple circle. Just goes character by character. So we get that, compare against the end of the string marker, and until that is the case, we just print the character on screen. So to see that in action, let's call the B command and give it